Hello, so in this video we will talk about the relationship between regular grammars and regular sets. So as a recap, we will study the definitions of these both terms and then we will see what is the relationship between them. So again, for a regular grammar, let's define a grammar first. So grammar is composed of a vocabulary, a set of terminal symbols, a set of symbols, and a set of productions. So what is T? T is the subset of V, which is consisting of terminal elements, elements that cannot be replaced by other symbols. And what is S? S is the start symbol, and it is also a subset of V. And what is P? P is a finite set of productions which specify the rules for replacement of one string in the in V star by another. What is V star? V star is all the combinations of all the elements in V. Okay, so then in other words, Z0 arrow Z1 means that 0 is replaced by Z1. Okay, and then the set V minus T or V take away T is denoted by N, which is non-terminal elements. And every production in P must contain at least one non-terminal element on its left. So this means that the rule of production in general is that this guy should have at least one element which belongs to N. Okay. Okay. Now we talk about, since we are talking about regular grammars here, so for regular grammars we have the following rules of production. We have W1 is replaced by W2, where W1 is any non-terminal element and W2 is a concatenation of A and B. And what is this small case A? Small case A is a terminal symbol and B is a non-terminal symbol, and uh, W1 is a non-terminal symbol. Okay, and we can have another kind of production, which is W2 is just A. So then we have a non-terminal symbol replaced by a terminal symbol. Okay, and another option is that we have a starting symbol which is replaced by a lambda. And what is lambda? Lambda is the empty string. So we will just write it again, empty string. Okay, and then we know that this AB is belong to non-terminal set, and small a or under lowercase a belongs to the terminal set. Okay, now let's define regular sets. So regular sets are those sets that can be represented by finite state automaton. So we have seen it already that from Kleen's theorem, it's regular sets and the sets represented by the finite state automaton are the same. So although there are other definitions of regular sets, we'll use this definition for our sake in this part of the video. Okay, so how do we define a finite state automaton? We define it by S, which is what? Which is a set of states. So, and what is I? I is the input alphabet. So I means that it represents the set of inputs. What is F? It's a mapping of S and I to S. So for each input and state, we can get a next state. Okay, so determine next state from current state and input. What is S0? S0 is the starting state. And what is F? F is the set of states which are accepting states or final states. Okay, and obviously this F is a subset of the total number of the total states. Okay, and in terms of representation, if we draw the transition diagram or the graph of this, so then final states are usually represented by double circles. Okay, now we come to the main part of our lesson here. So we want to prove that a set is regular if and only if it can be generated by a regular grammar. Okay, so let's break this proof. So to prove, we break it into two parts. So let's say that this part is P and this part is Q. Okay, so now for the first part we prove, so we prove like this. We prove Q implies P. So in other words, what do we want to prove? We want to prove that if this, then this. So then I will say if a set is generated by a regular grammar. So I'm just repeating it, although it's not needed, but just to show that this means this, then it is regular. Okay, इसको edit करेंगे बाद में. Okay, so then this means that we are given this information and we have to come up with some relationship which leads to this information. Okay, so what is the strategy? So strategy is that we build a non-deterministic finite state automaton that accepts the same language as language of our regular grammar. Okay. Okay. So how do we do it? This is how the proof goes. This is how the set of rule goes. Okay. So if we have, so we say if x is a part of a non-terminal symbols in G, then create a state which is xs sx, which obviously belongs to S in my non-deterministic finite state automaton. Okay, and also create S0, which is starting state, and SF, which is the final or accepting state or accepting state. Okay. Okay, and then rest of the productions. So now if we have a production like this, A is replaced by A. This is my grammar here. So this actually this transforms to, so now I'm talking about the F here. So this corresponds to that, the set of state, the state which corresponds to this A goes to the final state at an input of A. Okay. And then if we have this kind of production, then we have SA, A, SB. And then if we have this production, then it goes to this story. Okay, so then if S goes to an empty string, then our starting state is also an accepting state. So using these rules, these set of rules, we can convert any regular grammar into a regular set. Okay, now let's see how is it possible. Okay, so now we have these productions as our regular grammar, and we have the set of terminal elements and set of non-terminal elements. Okay, so now then what is our corresponding state machine? So obviously we will have an S0. Whether it should be an accepting state or not, it should be because of this guy. So I will draw another circle around it. Okay, then I should have a state for A, and I should have a state for B, and I should have a final state, which is SF. Okay, now what does it mean? S goes to 1A. So this means that an input of 1, I go from the starting state to A. So then this guy is at 1. Okay, then S goes to 0. S goes to 0 means that this guy goes here. That's it. And then I have, so this is taken care of, this is taken. Then A goes to 0B. So this means that at an input of 0, I go from A to B. B goes to 1B. This means at an input of 1, I go here. And B goes to 1. It means at an input of 1, I go here. Okay. So then this guy is the corresponding, finite state automaton for this guy. Okay. Okay. Is this deterministic or non-deterministic? Hmm? So this is non-deterministic because I don't see an input of 1 coming out of this one. Okay. For a deterministic, we should have all the inputs for each state defined. The next state for each input and state pair should be defined. But there is no next state for input of 1 with a present state of A. Okay. Anyways, so what is the language? What is L of G? So now for S, from S we can go to 1A. So let's see. So this is, let me do it here. So 1A, and then A can go to 0B. So I can say 10B, and then B goes to 1B, and B also can go to 1. So it can be 101 or then 101B, and then this can be just 1 or 1B. So 101 1B and so on. So what does it mean? It can be just 101 1111. So this can be any number of ones. So I can say 101 where n is greater than or equal to 1. Okay. And then we have obviously we have s goes to 0. This is also the case. And s is an empty string. So this is also the case. And then I can also say 101. So this is any number of ones more than 1, right? So I can also use the clean closures as symbols here. So this makes sure that we have 0 or more number of ones, and then we have 1 here. Okay. So this is the language here. So I should say this is language of the grammar. What is the language generated by this finite state automaton? So let's see. So now this starting state is the final state as well. So this is the case. Now the starting state goes to a final state at the input of 0. So this is the case. Then we have 1, 0 and 1. So 1, 0, 1 is the case. But then we have a self loop at B, right? So I should say 1, 0, 1 star and 1. Because this we already saw in the proof of Kleen's theorem that if we have to remove this state, then this self loop will lead to 1 star here. So we'll have 0, 1 star and 1. So 0, 1 star and 1, and this one is represented by this one. So this guy and this guy are the same. Although this is 1 star here, I can also say this is the same language as 101 star 1. Okay, so this is the same part. This and this represent the same thing. So this, in other words, what we have shown is we have shown that if we draw our non-deterministic finite state automaton using these rules from a regular grammar, we will always be able to draw it. Okay, and when we are always able to draw it, then this means that we will always end up with a regular set. Okay, so this is this part of the proof. Okay, now this was my P and this is my Q. Okay, now we want to prove this part. So in other words, what do we want to prove? We want to prove that if a set is regular, there is a regular grammar that generates it. Okay, so now we are given this. Um, we are given the state machine as the final state automaton, which is S, I, F, and S0. Okay, so this is my state machine, final state automaton. So now we want V, S, T, and P. Okay, this is my grammar here. So my rules go like this. So then my vocabulary is made from the input alphabet union the set of states uh, in the machine. Okay, and my terminal symbol is just the input alphabet, and my starting state, the starting symbol is the starting state, and my productions. Okay, so then the productions. So if we have a situation like this, SA, SF at an input of A, so I change it to A. So you can appreciate that we are doing the exact opposite of what we did in the first forward part of this or previous part of this theorem. So then if we have SA, so if we have SA at SB, so this means I will just change it to A. Okay. Now if, for example, if we have, we will include this if my starting state is a subset of, is an element of the final states. Okay, and we can also say that the language generated by the machine has the empty string, which is the same thing. Okay, now again we can appreciate it that the language generated by this grammar will be the same as the language generated by the machine, by the automaton here. Okay, this is because if we can start from a starting state and then end up with the final state and get the same symbol, as we can start with the starting symbol and end up with some terminal symbol. Okay, okay, so we have this machine here and this is my starting state here. Okay, so then we have to find a grammar that generates the same language as this. Now we will use the same rules here. So what is our V? So let's say we have a symbol A which corresponds to this. We have a symbol B that corresponds to this, and we have a symbol C that corresponds to this state. Okay. Then what is V? V is equal to a set of inputs, and inputs are 0, 1, and then A, B, C, and then of course S for this guy. So I can say S here. Okay. So what is my terminal symbols? Terminal symbols are 0 and 1, and obviously non-terminal symbols are A, B, C, and S. Okay. So now productions. So productions are what? Okay. Now S0 at an input of 1 goes to a terminal state. So then this means that I would say S2. Correct. Now S0 with an input of 1 goes to S3. So I say S1C. Okay, because C is corresponding to this. And then this is taken care of. Okay. Now A. So A at an input of 1 goes to a terminal state. Okay. But A at input of 1 also goes to itself. Okay, so we have to take care of those two things. So we have to say here, because this is kind of a clean closure kind of a situation here. And at A at an input of 0 goes to C. Okay, so A at input of 0 goes to C, so I should do this. Now C. So C at an input of 0 goes to itself, so I should say C goes to 0, C. Okay. And C at an input of 1 goes to a terminal state, so C goes to 1. Okay. And then B. So B goes to 0, B goes to 1, because B itself is a terminal, accepting state. So then B goes to 0B and B goes to 1B. So these are all the productions which correspond to this. Now again, starting from any starting state here, we can traverse the path which leads us to the final state or accepting state, and we can from here, starting from any starting state, starting symbol, we can traverse the path to go to any terminal symbol. And we will see that's due to our rules here. We can see that the language generated here and language generated here are the same. So this exercise is exactly the same as we did in the forward path of our theorem here, or the backward part of the previous part of this theorem. And this can be done by the viewer easily. Okay. So in other words, as a recap, what we did was we proved that a set is regular if and only if it can be generated by a regular grammar. So we did the part when we took a regular grammar and devised a way to generate a non-deterministic finite state automaton using some rules from the production of that regular grammar. Then for the other part, we took a non-deterministic finite state automaton, and using some rules we generated a grammar which can lead to the same language as that of the non-deterministic finite state automaton. So since the non-deterministic finite state automaton is related to the regular set through Kleen's theorem, we can eventually say that a set is regular if and only if it can be generated by a regular grammar. So this is it about this proof. Hope it was comprehensive enough to understand. Thanks for watching. Hope you liked the video.